Right, in this video, we're going to talk about 3.1 Objective 1, where we analyze questions involving tangent lines and derivatives conceptually. So what is a tangent line as opposed to what is a secant line? So this formula that's given right here, the f of x minus f of a over x minus a, that's really the same thing as f of b minus f of a over b minus a that we had for the slope of a secant line in pre-calculus, the average rate of change. And the slope that you would get between 2 points. I just want point B, BF of B, to be a little bit more generic here. And I'm going to call it X, and I want that B value to be very close to, but not exactly A. So I'm going to let X approach A, but not get to A. And so this looks like a 0 over 0 situation, which would tell us to do some algebra and that we'd have this X minus A as a factor to cancel out. And that's exactly what's going to happen. And then we'll be able to find the slope of the function f at a. So we just talked through all of that, but the line through the given point a f of a and a nearby point x f of x is called a secant line. The slope of the line is given by the quotient right here, f of x minus f of a over x minus a. And as x approaches a, the quotient approaches the slope of the line tangent to the curve, meaning it's going to touch at that single point x equals a. So, and it's going to touch at a f of a. There we go. So the average rate of a function f over the interval a to x is f of x minus f of a over x minus a. Now that says plus. This one, f of x minus f of a over x minus a. As x approaches a, the average rate of change of f approaches limit as x approaches a of f of x minus f of a over x minus a. That's that one. This limit is the instantaneous rate of change in f at x equals a, and is also the slope of the tangent line. So this tangent line problem is a really big problem in calculus. It's one of the things that separates calculus from pre-calculus, is we could talk about secant lines in pre-calculus, but we can talk about tangent lines in calculus, given the now that we have the limit operator. Given a function f and a point a in the domain, what does f prime of a represent? That would be the instantaneous rate of change of f at a. It would also be the slope of the graph of f at a. Figure to the right shows a graph of f and a line tangent to the graph of f at x equals 9. So our a value there, just think a equals 9. That find f of 9. So let's look at the graph. It looks like it's 9, 3 from the graph there. F prime. Well, let's look at this line here, and it looks like we have some points that are definitely, looks like we go through 6, 9, looks like it's on there. So that'll be another point we can use. So let's use 6, 9, and what were we using? 9, 3. So f of b minus f of a over b minus a. That looks like -6 over 3 is a -2 for my slope. So I didn't want to pick something where I wasn't really sure of the x and y coordinates. I picked another point where I was sure on the graph that was crossing through one of these grids right here, that it was exactly an x and a y value that I could pick off of there. An equation for the line tangent to the graph f at the point 47 is y equals 3x minus 5. Find f of 4. Well, it's right there. They're going to have the tangent line and the function are going to have the same y value at 4. And then find f prime of 4. Well, that's going to be the slope of this tangent line. So that's going to be 3. All right. Moving on. Determine whether A through C are true and give an explanation or counterexample. For linear functions, the slope of any secant line always equals the slope of the tangent line. That is true. The linear function has the same slope everywhere on its graph, so its average rate of change of growth equals its instantaneous rate of change of growth everywhere. Let's see, statement B says the slope of the secant line passing through the point P and Q is less than the slope of the tangent line at P. Note, we just gave a counterexample. Well, the slope of the secant line passing through the points P and Q is less than the slope of the tangent line at P. The statement is false. So here's a counterexample. F of x is equal to x squared. The slope of the secant line passing through the points -2, 4, which are on F, and 2, 4, which are also on F, is 0, which is not less than the negative slope of the tangent line at -2, 4. So if we look at that, we have -2, 4. Let's show you what we're talking about. 2, 4, and here's a secant line that has a slope of 0, but this tangent line right here has a slope of, I'll tell you that slope would be -4, and 0 is not less than -4. All right, consider the graph of the parabola f of x is equal to x squared. For x is greater than 0 and h is greater than 0, the secant line through x f of x and x f of h is always has a greater slope than the tangent line. That's true. So let me draw the picture for that and show you what we're saying. So I'm only looking at the right-hand side of the parabola, and I'm picking a point that is here that's going to be x, f of x, and a point a little bit away from it that's going to be x plus h, f of x plus h. And I'm saying this tangent line right here must have a shallower, smaller slope than the slope of that secant line, because I can just analyze that with the picture, but I'm rising a whole lot more. I'm rising faster than I'm running with y equals x squared. And so it's always going to have a greater slope if I go to the right and up. I'm going up more than I'm going to the right. So that's going to increase my slope quite dramatically, even if I go to the right only a little bit. So B statement is true since the slope of x squared is increasing for x is greater than 0. The average rate of growth on the interval x to x plus h is greater than the instantaneous rate of growth at x. And I showed that with the picture and talked through it in terms of how that had to happen because y was changing faster than x was changing with the function y is equal to x squared. All right, that's it for this video. We'll come back next time and we'll talk about the limit, these limit definitions to find the equations of the tangent line. So this is going to start to talk about the limit definition of the derivative. We're still talking about the slope of a tangent line. We're not really calling it a derivative yet, but that is what we're talking about here. So see you for the next video.